So, let's look, now we know the representation, right? In many ways it's similar to decision trees, so this is not a big leap from decision trees. Now let's look at how we learn rules, right? And we don't have to do it from scratch. We already know how to learn decision trees. Naturally, learning rules should not be able to use a lot of the same ideas, right? So can anybody suggest how we might learn a set of rules by analogy with decision trees, or just, using whatever comes to your mind? How might we do that? And remember, we said it's a constructive algorithm, right, where we build one rule at a time and so on and so forth. So how might we go about it? Suggestions.
Learn a decision tree and convert to rules.
No, I couldn't agree with you more, right? So what's method number 2? That is a perfectly good method, right? That's what's in C4.5, right? You can do that. When Quillen did his data mining company and became a multimillionaire, actually, I don't know if he became a multimillionaire, but that's what he had, right? He was learning rules via decision trees, right? But let's suppose that we want to, learn rules directly, right? How might we do that?
Just start picking examples and make a very narrow rule, and then as you find more examples, like broaden the rules if it makes sense.
This is actually one option. We're not going to talk about it today, but this is often called the bottom-up or specific to general learning of rules. I actually did my PhD thesis in that, so it must be good. But anyway, right? Short of that method, which is a good one, but is not the most widely used one, what might we do?
I guess you could start with a rule that uses the least number of attributes and covers most examples.
Yeah, exactly. So this is the analog of initially, we have a tree that is empty and we pick the root, right? What we're going to do is we're going to start with a rule that just has the consequent and has no antecedents, meaning it matches everything. Everybody's a good credit risk. You give credit to everybody. And then you figure out, let me try each attribute in turn and add that as a condition on the rule. Right? Very natural thing to do. Let me test that and see if it gives me a more accurate rule. There's a good chance that it will. So I try adding each possible antecedent and I pick the best one. And then what do? Rinse and repeat. Right? Then I now have a rule with this antecedent and the consequent, and now I try every of the other possible antecedents that I have in addition to that one, and I find the best rule of size with 2 antecedents. And I keep going until when? Until when? What, sorry?
Until you don't see an improvement anymore?
Until you get no improvement. Very good. And what is the most natural case in which I get no improvement? In which, in fact, in the case of learning a rule, I know I can always get to that. Right? Remember, in the basic decision tree algorithm, when did we stop, growing the decision tree?
When you correctly classify everything.
Yeah, when everything on my training set was of the same class, therefore I don't need any more conditions. Right? Same thing here. Right? Initially, I have a big mixture of positive and negative examples. Right? I start adding antecedents, and notice what happens is that I'm adding an antecedent that throws out, hopefully, a lot of negative examples and very few positive ones. Right? So as I grow the rule, I have fewer negative examples until hopefully I come to a point where I have no negative examples, right? And my rule only covers positive examples, at which point it makes no sense to try to refine it more, and that's where I stop. Okay? So that is our algorithm for growing one rule. Very simple idea. Okay? Yeah?
So what happens if you have 2 examples with exact same values but different classes?
Very good. That can happen. That is actually the only failure case, right? Notice that as long as that doesn't happen, right? All my examples have different values. I can guarantee that I'll always be able to induce a pure rule, right? Because in the worst case, that rule's just going to add every antecedent corresponding to every value in that example, and then we're going to have it. If I have, say 3 examples like that, and 2 are of the positive class and 1 is negative, well, the positive wins, and the probability is 2/3. If I have 1 of each, which can happen, right? I have 2 patients with exactly the same symptoms and tests. One has tuberculosis, one doesn't. Well, at that point, you can flip a coin or maybe try something else. We can't tell.
But in rules, you can't represent that probability, right? You just have to choose one or the other.
No, I mean, like I said, you could, right? A basic rule doesn't have that, but I can, this is often done, right? I attach to each rule the probability with which the consequent holds given the antecedents. For example, if I'm going to vote among rules, that's probably a very useful thing to have. Okay, so as before, we have the problem of, we need a criterion to decide how good a test is, right? And before, for growing a decision tree, we looked at accuracy and information gain, right? And again, here in the case of rule induction, I have lots of possible quality measures for a rule, and people come up with new ones all the time. But again, just the accuracy of the rule is actually a very decent thing to use. Okay? It's actually used more for rules than for decision trees. Right? Because when learning a rule, we don't have this problem that we're trying to balance what happens between different branches. We just want that rule to be accurate. Okay? So I could just use the accuracy as a rule, right? Of the fractions of examples that the rule says are positive, how many really are positive? And that's my accuracy, right? I could just use that. So, if the rule covers M0 negatives and M1 positives, that would just be using M1 over M0 plus M1 as the criteria. Okay? There's other things that you can do. In particular, you can use the analog of the information gain. But notice that before, right, I was looking at all the values of the variable. At this point, actually, what we have is we can actually go back on the notion of gain and entropy and just think back to the surprise, right? I'm actually now growing a rule to predict a particular class, right? So what I don't want to have is nasty surprises, right? I don't want that when my rule says it's spam, it's actually not spam, okay? So what I can do here is actually not maximize, gaining the absolute, but just like minimize my surprise. So here's my old surprise, and here's my new surprise. Okay? So remember surprise was P log P, right? Or the expected surprise, right? For this particular case, right? This is actually what I'm trying to improve on, right? So the difference between the old one and the new one is my reduction in expected surprise. Okay? When I'm in this situation where I'm saying that the rule is 1. Okay? Now notice that there is only one part of what I have here. I've also put this M1 prime here. M1 prime is the new number of positive examples covered, and M0 prime is the new number of negative examples covered. And I've multiplied my reduction in expected surprise by M1 prime. Why would I do that?
If your rule covers 100,000th of your data set really well, do you really care?
Precisely. It's really easy to induce a rule that looks really good, namely, say, a rule that covers only one example, right? It's 100% accurate. You've got the maximum possible reduction in surprise, and yet that rule sucks. Why is that problem happening here and it didn't happen in decision trees? Remember, in decision trees, when we branch on an attribute, we're looking at both sides, right? And we're balancing what happens on both sides. When we're learning a rule, no, we're only looking at this one side. So we just throw out all the negative examples we can, and then we get a rule that is totally overfitting. What is a sign that we might be overfitting?
M1 prime gets quite small.
Precisely, right? The fewer examples the rule covers, the more suspicious we should get. If the rule covers 100,000 examples and they're all positives, we're pretty confident that that region that the rule covers is just positive. But if the rule covers 2 or 3 examples and they're all positive, well, you flip 3 coins and they could all come out 1. So a very simple thing to use, as a fix for this, is to actually multiply the gain by the positive examples that the rule still covers. Okay? We want that to be large, and if the surprise reduction is big at the expense of making this small, then this rule is dubious. Okay? This is just a heuristic, but it's very important to use something like that. Okay? We will see many different ways of combating overfitting, but this here, in a simple way, is one way of combating overfitting. Okay? Questions? Okay, so at this point, we know how to induce a single rule. Okay? So with this algorithm as a subroutine, what should our algorithm be for learning the whole rule set? Right, we're almost there, but we need one more step. Right, so I have a black box that returns the best rule that we can find. What should I wrap around that black box to induce a set of rules, not just a single rule? Here's one way to think about this. Okay, I just learned my best rule. Okay, I have a rule now. So what do I do next?
So get rid of all instances that satisfy that rule and then pick the next best one.
Yeah, exactly, right? I now need to learn my second rule, right? And I don't want to go induce the same rule again, right? But my goal with the second rule and the remaining ones is to account for the instances that the first rule didn't account for, right? The positive instances that were correctly classified by rule 1, well, they're taken care of, they're covered. Okay? So what I do is I take those away, and now I have a new, smaller training set, and now I go find the best rule on that training set. Okay? And I keep on doing this until when? Again, don't worry about overfitting for just a second. When should I stop?
And all positive examples fall under some rule.
Precisely. Once I've accounted for all my positive examples, there's nothing left to do. We're done. Okay? And this is our algorithm. Also known as separate and conquer, right? By analogy with decision trees. Decision trees are divide and conquer, right? I divide my set into smaller and smaller pieces and I conquer them. In rule induction, what I do is I conquer one piece, I separate that out, and then I go conquer the rest. Okay? And that's, a complete rule induction algorithm. Any questions? Yeah.
What if you have just positive and negative classes right now? Could this be extended to like multiple classes?
Absolutely, and we're going to talk about that in a little bit. But as a background process, you can figure it out and then tell us. But you're not allowed to look ahead in the slides. Look ahead is sometimes used in machine learning, but it's very expensive. Any other questions? Okay. Now, in the case of decision tree learning, greedy search works fine, and it's what people almost always use. In the case of rule induction, that is not quite the case. Pure greedy search actually can give very bad results in rule induction because it can get very quickly stuck in a very bad local optimum. Okay? So for rule induction, there's a couple of other things that people often do that are worth knowing about. Okay, so let me just briefly mention those. The first one is what's called round-robin replacement. And this has to do with the fact that if you think about it, the first rule has an unfair advantage. It's not competing with anybody. It can account for everything that it wants, and then it leaves very little data for the succeeding rules. Right? If there's some data that is covered by two rules, right, once the first rule took care of it, now the second one doesn't have access to it. So I've unnecessarily restricted the data that the second rule has access to. Okay? So what can I do about that? Well, what I can do is I can induce a bunch of rules and then say throw away the first rule and see, well, let me now induce something in the presence of the other rules and see what that would be. If it's the same rule again, then fine. But typically it won't be, because now the other rules have accounted for part of what that rule accounted for, and so now this one can be different. Okay? So this is called round-robin replacement. I can also do this process sort of like as I go, as I add each rule, I try removing rules. There's many variations of this, but some of the best rule induction methods do something of this flavor. Okay? But the most important thing to know about is this last one, beam search. Does anybody here know what beam search is? Beam search is a less greedy search. In greedy search, what happens is that at each point I pick the best antecedent, and then I run with that, and I never look back. And you can get into a lot of trouble that way. In beam search, what you do is the following, is at each point I pick the k best antecedents, and I form k candidate rules. K is called the width of the beam, right? It's called a beam. It's a beam because it's like having a flashlight with a wider beam as opposed to just a pencil of light pointing in that one direction. Okay. And then what I do is I try adding each new antecedent to each one of those, right? So now instead of 10, I have 100 candidates. And now again, I find the best 10 of those. Okay. And I keep going in the usual way. And then finally, of the 10 best that I have at the very end, when there's nothing, no improvement to be had, I pick the best one. Okay? So what is the relationship between beam search and greedy search?
Greedy search is a beam of one.
Exactly. Greedy search is just what you get when the beam is one, right? They only keep the best one. What is the advantage of beam search over greedy search, right? When will greedy search and beam succeed? Think of the second best, right? The one that greedy search threw away. It could be that second best conjoined with the next attribute now becomes the best. Okay? In fact, that can happen a lot, and that's why beam search can be a very worthwhile thing to do. It's more expensive, right, by roughly the order of the size of the beam, but you can get much better results that way. So the typical method that people use in rule induction is actually beam search, not greedy search. If you just do greedy search, you could wind up with a very bad rule set. And usually what happens is that you get stuck right away. You don't actually find any good rules because the concept is pretty complicated, and then you don't know what else to do. Okay? Questions? All right, so